Hey there, and welcome to This Explainer. Have you ever actually stopped to wonder how water from a massive lake just evaporates into the sky to form rain? Or how a single tiny drop of dye can completely change the color of an entire glass of water? Well, today we're exploring exactly that in The Invisible Flow, Demystifying Mass Transfer. We are going on a seriously fascinating journey together. We're going to start incredibly small, looking at invisible, microscopic, molecular collisions, and then we're going to scale all the way up to see how those exact same tiny movements literally govern massive atmospheric weather systems. It's going to be a fun ride.
Okay, let's dive into this. Here is our cognitive roadmap for today, so you know exactly where we're headed. We'll start with Section 1, the basics of mass transfer. Then, Section 2 covers Fick's law of diffusion, followed closely by Section 3, gases, liquids, and solids. In Section 4, we'll tackle the mass transfer coefficient, and finally, we'll wrap the whole shebang up with Section 5, atmospheric evaporation.
Section 1. The basics of mass transfer. We're starting at the very foundation here.
So what exactly are we talking about when we say mass transfer? Well, at its core, it's pretty much exactly what it sounds like. It's the transport of mass from one place to another. But, and this is key, it actually encompasses two wildly different scales. We're talking about large-scale macroscopic transport, like a bulk fluid rushing through a giant pipeline, and we're also talking about incredibly tiny microscopic movements where individual molecules slowly diffuse across a concentration gradient. It's both.
So the crucial point is understanding this basic dichotomy. On one side, we have the macroscopic level, right? That's convection. This is bulk mass transport. Think of a strong gust of wind carrying moisture through the air, or water being forcefully pumped through a municipal system. We usually treat that as fluid mechanics, but on the other side, we have the microscopic level, which is diffusion. This is happening purely on a tiny molecular scale, where molecules just naturally move from regions where they're highly concentrated to regions where they aren't. To really get a grip on mass transfer, you have to realize it's the howling wind blowing outside, and it's also the perfume slowly, silently spreading across a quiet room.
Moving on to Section 2, Fick's law of diffusion. Let's look at the micro-level rules.
Okay, picture this setup in your head because it tells a really profound story about how math models our reality. Imagine a completely sealed box, and right down the middle, there's a super thin partition. On the left side, you've got gas A, on the right side, gas B. Now, what do you think happens the exact second we yank that partition out? The molecules definitely don't just stay put. Because they're in constant jittery motion, they start bouncing all over the place. Through purely random molecular collisions, gas A diffuses right into gas B, and gas B diffuses right back into gas A. They're going to relentlessly keep mixing and colliding until a perfect equilibrium is reached, and the concentration of both gases is totally uniform throughout the entire box.
Now, what's really interesting about this slide is how Fick's law translates that physical chaotic mixing into a neat mathematical concentration profile. When you look at that downward curve, Fick's law is basically stating that the mass flux of a constituent per unit area is strictly proportional to the concentration gradient. In plain English, this math elegantly proves that molecules will always naturally flow from a highly crowded packed area on the left right down the gradient to a much less crowded area on the right.
You know, if you look closely here, notice the profound symmetry in this comparison. It's actually a great analogy anchor. The math governing mass transfer, that's Fick's law, is structurally identical to equations you probably already know. It perfectly mirrors Fourier's law for heat conduction, and it mirrors the viscous shear equation for momentum. Think about that for a second. Whether you're transporting heat energy, fluid momentum, or actual physical mass, nature is literally using the exact same underlying logic. A driving force simply pushes something from a high concentration to a low concentration.
Which brings us to Section 3, gases, liquids, and solids. Let's see how the medium changes the rules.
There is a really stark contrast depending on what state of matter these molecules are actually traveling through. In gases, diffusion rates are incredibly high. I mean, gas molecules are totally free to just zip around rapidly, and their diffusion coefficient is heavily dependent on temperature. So the hotter it is, the faster they move. Simple enough, right? But in liquids and solids, the diffusion rate absolutely plummets. Why? Because the molecules in liquids and solids are packed so tightly together, they create these massive invisible molecular force fields. These force fields heavily restrict any freedom of movement, meaning a molecule literally has to fight its way through just to shift positions. It's like trying to run through a crowded concert instead of an empty field.
Section 4. The mass transfer coefficient. Time to bring in the engineering tools.
So to actually make precise, real-world calculations, engineers use something called the mass transfer coefficient, which we represent with the letter K. Now, K is a proportionality constant that links the diffusive mass flux of a component to its concentration difference across a boundary. If you remember our analogy from just a minute ago, K is simply the mass transfer equivalent to the heat transfer coefficient used in thermodynamics. It just gives us a very concrete, measurable number for how easily mass can move through a specific boundary.
And this brilliantly illustrates how deeply interconnected all these physical phenomena really are. Engineers rely on these connective, dimensionless numbers, the Schmidt number and the Lewis number. The Schmidt number is just the ratio of momentum diffusivity to mass diffusivity. The Lewis number? That's the ratio of thermal diffusivity to mass diffusivity. They literally act as the connective tissue between velocity, temperature, and concentration profiles. It just proves once again that heat, mass, and momentum transfer are all part of the exact same physical family.
Finally, we reach Section 5, Atmospheric Evaporation. We're zooming all the way out now.
But before we look at the solution, I really want to pose a question to you. If we have all these perfectly elegant, beautiful molecular equations, like Fick's law, why can't we just plug those numbers in to predict tomorrow's weather, or precisely measure how fast a real, natural lake is evaporating?
Well, the answer is that nature is chaotic and, honestly, incredibly messy. Our purely analytical, perfect molecular equations, they work beautifully in a controlled, perfectly stilled test tube in a lab. But out in the open atmosphere, those simple equations completely fall apart. We're dealing with substantial, unpredictable, turbulent eddy motions. The diffusion coefficients vary wildly depending on your altitude. And of course, we have continuous, unpredictable wind currents. The bulk macroscopic transport out in the real world is so intense that pure microscopic diffusion math just cannot keep up.
Let's move to and see how this builds an ingenious, empirical engineering solution. Since engineers couldn't just rely on pure analytical math to tame the sheer chaos of the atmosphere, they created this, the Standard Class A evaporation pan. It's not a complicated computer model. It's a strictly standardized 4-foot diameter metal pan that they physically place right out in the environment to observe actual evaporation in real time.
And here's how they actually crunch the numbers for environmental evaporation. They measure the daily wind movement specifically 6 inches above this pan's rim, and they calculate the local vapor pressures. Then, they take that real-world pan data and multiply it by a standard pan coefficient, usually 0.7 if the pan is sitting on land, and 0.8 if the pan is floating out in a body of water. By relying on these actual physical measurements rather than just isolated, perfect equations, engineers can highly accurately predict large-scale environmental water loss.
So, think about the journey we just took. We started off by discussing invisible gas molecules bouncing off each other in a tiny little box, and we ended up predicting how millions of gallons of water evaporate into our global atmosphere. So, what does this all mean? How does the continuous, completely invisible cycle of microscopic molecular diffusion ultimately govern every single environment and life form on Earth? I mean, every breath you take, every rain cloud you see in the sky is entirely dictated by these relentless, tiny collisions. I really hope this explainer leaves you eager to look at the invisible world all around you just a little bit differently today. Keep wondering, keep learning, and I'll catch you on the next explainer.